Welcome everyone to the Virtual Storage Developers Conference. My name is Bill Gervasi. I'm the Principal Systems Architect for Nantero, and I'm going to be talking today about an automotive SSD application that I'm working on. Let's go through the agenda. What we're going to do is start talking about cars. We've seen phenomenal changes just in the last decade or two in the feature sets of these cars. So let's take a look at those applications and try to intuit what are the solid-state drive requirements for such a vehicle. I'm going to be showing you a standard that is in development that is not just a JEDEC standard, but is also incorporating the requirements from multiple standards organizations that are coming together to bring this to the market. I'll give you some insights as to where our thinking is about this standard and some of the features that we believe will be necessary. And finally, I'm also going to show you what are the topics for debate, give you a call to action to get engaged with us and to help finalize this specification. But let's start with the cars. Over the last couple of decades, we've all seen how cars have changed tremendously. We've seen how they've incorporated displays and GPS and all these other fantastic features. But in order to do this, they need essentially supercomputer power in order to keep the car not only functional, but safe as well. And by safe, I'm talking about a lot of features. There are many, many sensors inside today's cars. There's no one sensor that does everything. Some are better in snow conditions. Some are better at night, some are better during the day. So you need to have a variety of sensors, which means each of these needs to be streaming a bunch of data back to a processing unit. In addition to monitoring the outside of the car, there's still a phenomenal number of sensors inside the car. The temperature of the batteries, the charging and discharging, the engine brakes, all of that stuff all requires horsepower to keep monitoring the system. In addition, cars are very networked. They are communicating with a large number of external sources, for example, the internet. Also, they're communicating with other cars around them. They're communicating with streetlights. In the future, these cars are going to be communicating with a phenomenal number of devices external to the car to keep that car safe and to keep everyone around the car safe. The in-vehicle entertainment is also exploding. We see that the displays are becoming more sophisticated. You can be watching movies in the back seat of the car to keep the kids entertained. There's so many things that can be floating around this car. Throw in the maps and traffic information, and you're talking about devices that are now processing 300 gigabytes per second of data. So let's imagine that as the backdrop and see, what does an SSD for this environment need to look like? Well, the storage requirements are fairly standard. It's about ranges from, say, 128 gigabytes to 4 terabytes of data. And with that kind of range, pretty much in the sweet spot for today's solid-state drives. So let me tell you a story. I was driving down 280 one day in my rental car, and it was a rainy day in the Bay Area, going about 65 or maybe 70 miles an hour, and all of a sudden, a lightning bolt struck about 100 feet off the side of the road. My rental car screen went completely blank and then slowly started to reboot. I had no idea what to do. I just held onto the wheel, didn't try to steer, didn't try to brake. Finally, the music came back on, the display came back on, but for that 5 to 7 seconds, I was absolutely in limbo. I had no idea whether my car was functioning or not. This is the environment that we're working in, where the requirements for that car to come back online as quickly as possible is going to be one of our major goals. So let's look at what happens here. So you have the communications, you have all these displays, you have the entertainment and vehicle control all around the car. You have these displays, and now we're going to talk about what is that shared resource that all of these execution units are going to require. These devices are typically going to be separate devices. You're probably going to have 3 to 4 system on a chip devices sharing this central resource. So obviously we want high performance. That 5 to 7 seconds that I was waiting for the system to reboot is not exactly very favorable. I would like to see a much higher performance system that's going to come back online much more quickly. The temperature ranges are very important to an automotive design. You want to be able to park your car in a parking lot in Saudi Arabia or in Nome, come back after a vacation, and you do want your car to still run. So that temperature range needs to be pretty wide. Cars are increasingly expected to last a long time. The cost and complexity of a car is going up. People would like to see cars that last maybe 10 years, 17 years. And so the long life expectancy is kind of like antithetical to how SSDs operate in today's environment. Also want these cars to be very secure. The last thing that you want is for somebody to hack your car while you're driving down the road and suddenly change your GPS directions to steer you into a ditch. And yet, with all of this increasing functionality, you need to have a reasonable price point. This thing needs to be affordable for everybody. So here's what's being proposed. We have a new solid-state drive for automotive applications that is going to be a soldered down solution. No socket is allowed here. So this thing is going to drop into the footprint for the systems and allow that range of opportunity. So now, here's where I'm going to pause a moment and say, keep in mind this is a standard that's still in development. I'm presenting to you something that is not fully approved, and that's on purpose because the call to action here is to help us complete this specification and get it rolling out there. So what I'm going to be showing you is a work in progress, and things will definitely change before final approval. Okay, so with that as my disclaimer, let's look at what we do have a fairly solid grip on so far. The automotive SSD specification is being developed in JEDEC in the SSD committee, JC64.8. So that is where the master specification will be written. However, it's going to reference a large number of other specifications, including other JEDEC specifications, such as the temperature specification. However, that BGA package that I just flashed on the screen comes from the PCI SIG. This is a result of the M.2 work that's been going on in PCI SIG. We're going to leverage that both for simplicity of the design and multiple sources, but also so that we don't have conflicting standards in the industry. We want to help converge the industry requirements to drive the volumes up and bring the price down. The command set is going to include the NVMe command set. And that's going to give you extended features like the management of the media itself. Electrical specifications. This is again coming from the PCI SIG. We're looking at leveraging the PCIe work that has been done there. One of the features that JEDEC is going to be defining strongly is the concept of an extended terabyte write. This is the number of writes that can be performed on a drive during a day or over the lifetime of the drive. And where even industrial applications might require maybe 8 or 9 years of operation, cars are much longer term. You might need something that needs to survive for 17 years. And in 17 years, a phenomenal amount of data can move. And so we need to have a solid specification on how this device is going to operate over the lifetime of the car. With many requesting units, you have the communications unit, you have the screen displays, you have all these other units that are sharing this resource. One of the things that helps a shared resource work is I/O virtualization, where each of these requesting units can request portions of that drive and operate on those portions of the drive as though they owned it. Security is a critical function. The DMTF has done groundwork for the industry in terms of how authentication is done so that people can't hack into your car and modify it. As much as I think I would love to go in and reprogram my wife's GPS to say things like, did you really mean to turn left? I told you to turn right, but that's another story. We don't really want people hacking our cars. Sustained write is another feature that JEDEC is going to be engaging on. This has been in the industry a while, the idea that you need to be able to absorb data blocks of a certain size without interruption, even under stress conditions like, if you're having a flash device, sometimes you have to do wear leveling. So this sustained write feature says that even with that background stuff that needs to happen, you need to be able to absorb a certain block size. So that might be measured in, say, megabytes or gigabytes per second over a period of, say, 60 to 90 seconds. And then that translates to a file size that needs to be sustained without interruption. Key management is a part of the security features, and the OASIS group has been defining that. And then, of course, you want devices that are testable. And so JTAG from IEEE comes into play. So as you can see here, that even though JEDEC is driving the specification, we're going to be relying on a lot of organizations. So that begs the question, what does this standard look like? And why JEDEC? How is it that JEDEC fits into defining this standard? Well, it has to do with that previous slide. There are a lot of groups. There's SNIA, NVMe, there's PCI SIG, IEEE. All of these organizations bring pieces of the puzzle together, but no one group has everything. So JEDEC seemed as logical a home as any to bring this all together and to develop this for the industry. So now let's talk about how we're going to take these standards and make something that is easily consumable for the user. And so in this context, what we're going to say is we're going to take these other standards like the PCIe based protocol. We'll take the IO virtualization. We'll take the authentication work. And if you took all of those standards and just glued them together, you would have something that was unmanageably big, very expensive to implement if you could implement it at all in today's technologies. And it really wouldn't be solving the problem. So what we're going to do is take these specifications and apply restrictions to some of the feature sets. And then we're going to make a few extensions to them that will be specific to this application. So examples for that, the BGA package. We standardize on the footprint of a 28 by 28 millimeter package in the car. And then vendors know what footprint that they can fit into and what pinout to support. Similarly, we might go with PCIe 4.0 with a by 4 interface to hit the data throughput requirements we need. And so then that restricts the PCIe so that we're not going to be supporting, say, by 8 or by 16 options. We specify to the industry, all you need to lay out is a by 4 interface. We might put restrictions on the number of virtualizations supported in order to simplify the logic inside the auto SSD. And then we'll strip out functions that are simply not needed or are out of date. Now, this is an interesting debate because if you've done work in a standards organization, I'm probably speaking to the choir here, that standards are always hard to come by. You need to get suppliers who really don't like standards. They would love for customers to be locked into a single source solution. Then you have end users who would like to have every part in the industry be absolutely identical so that it simplifies their implementation. And this tug of war is actually very healthy. And this standards effort is no different at all. I am constantly arguing both sides of the equation to find out where's that middle ground where we can agree on something that can be mass produced. And so for a user perspective, they would really just love to have multi-source drop-in compatible devices. And we are going to meet that requirement. for all the reasons that you would be expecting. You would like to have at least 2 suppliers for every component, and you would like to have competition on price and support levels. Standard marketing. However, we also want supersets to be supportable. That core functionality that defines the Auto SSD is great, and that helps supply that market. However, it's not the only market in the world. There are other markets like tablets, like communications devices, that might be interested in the feature set that we're pulling together. And so what we're encouraging suppliers to do is go explore those markets and find the places where this automotive SSD could also be used in an industrial application, for example, and thereby grow the market and again, bring the price down. As long as these extended functionalities don't make the devices non-interchangeable, because that is a requirement for the car designers. So let's drill in a little bit on what the specifications look like on the inside. Here's the BGA package, 28 by 28 millimeters, 0.8 pitch, so it's fairly relaxed for standard printed circuit board technology. We defined a fairly large package because of that range of capacities that were desired. We saw that from 128 gigabytes up to 4 terabytes, pretty wide range. So you might need to have multiple die inside the package. Also, with a PCIe interface, 4.0 now, maybe moving to 5.0 in the future, you recognize that there's a power dissipation that you're going to need to deal with. So need to have a large enough package to get the heat out of the package as well. But suppliers don't necessarily want to have that 28 by 28 millimeter package for even their low-end 128 gigabyte drive. So what we're defining is a superset capability where you can have a small component, say 16 by 20 millimeters, that fits on the inside of that footprint. Maybe for your next capacity up, you go to a 20 by 24 package. There's also a 22 by 28 package, and then finally the 28 by 28 package. So from the car designer perspective, you design to the 28 by 28 footprint, and you can take all of these capacities. So you can do one design that can take many suppliers. And why is it? Because there's a lot of stuff that goes in there. There's the on-chip voltage regulation that might need to go in for some suppliers. The superset features might take space. So that's why we need to have that variety of packages available from the supplier standpoint. As long as end users choose the biggest footprint, everybody's good to go. Also wanted to highlight something that was not a goal. Initially, when we started the program, we thought we might have a standardized heat spreader. And turns out that that was not what end users wanted. So our current perception of what the car designers want is no heat spreader on that, just a BGA package, and they will integrate the thermal solution into the rest of the system. Get back to us if you disagree. And I think we can all agree that we want these cars to operate fast. We want them to come back online as quickly as possible. So here's our current thinking on what that's going to look like. Let's start with the raw data throughput. The raw data throughput with a PCIe 4.0 interface running with 4 lanes gives you a 64 gigatransfer per second peak throughput. Okay, that's a good performance number to start with. In addition, there are SSD-specific signals that help manage the device. An SM bus, system management bus, that can communicate with the device for telemetry, for configuration, and that sort of thing. And then, like I said before, the JTAG interface for doing manufacturing testing. So those are the interfaces that we're looking at in that package. Power is a little bit of a different story. This is an instance where I'm showing you where we're taking the PCI SIG specification that had historical baggage, if you want to call it that, in supporting things like a 3.3 volt rail. Well, in modern generations of silicon technology, it gets hard to support a 3.3 volt rail. So we've struck that off the list. We've struck 1.8 volts. We've struck 1.2 volts off of the supply rails. And so now what we're doing is focusing in on the lower voltage because, again, this is a more modern device and we don't need some of those older voltages. Looking at the temperature grade, this is a major area of debate right now. The car guys would love to go from -40 to plus 115 degrees C. Flash guys are really, really iffy on 115 degree operating temperature for a flash device. So one of the things that we're considering it to help the suppliers meet this end user requirement is to do performance scaling by temperature. And so by building a model of how the device operates at various temperature bands, the car designers can come up with models for how their cars will be used in order to use those devices and maximize the device lifespan. The sustained write throughput, we covered that in a little detail, and the extended terabyte write. So all of these features are coming together in that context of the temperature bands and the expected reliability of the drive. And those environmental considerations, it's a pretty long list. It's not just the temperature extremes, but we have to design around things like humidity and pressure and vibration and shock and all the other things that happen to a vehicle. These things need to be taken into account to provide a reliable device. So sustained write throughput. Like I said, this is the transfer rate times the time period. And right now, what we're seeing in the industry is a best of breed number somewhere around 3,100 megabytes per second for a period of 60 seconds for 186 gigabyte transfer size. This is one of those things that's going to not only be debated in the task groups, but will be evolving over time to try to improve that number. The extended terabyte write and drive writes per day parameters are based on the device capacity and how many years of operation that thing's going to be in use. So if you're looking at an auto lifetime of 17 years, then you look at the capacity, you start to come up with a model for how many writes are going to be done. Also, you need to look at what is the model of usage that you might have a device that's only used 2 hours a day, and the other 22 hours of the day it's in power off or in standby. So all of these things need to be taken into account for the model. Now, this is a case where we may find ourselves degrading this as the temperature goes up. So this might be how we achieve 115 degrees C, is that we say that at 115 degrees C, you're going to drop down to so many drive writes per day. But if you can keep that temperature better under control, you get improved performance. And then it becomes a designer problem. And usage models are not static either. I mean, today you pretty much have one car owner for one car. And this is starting to evolve over time. You're getting more and more shared vehicles on the road. And eventually, we're expecting that we're going to be seeing robo-taxis take over. This is a car that essentially drives from house to house, picking up random people for that shared resource. So here's a case where the usage model is literally changing in the next decade or so. Similarly, you have delivery truck drivers that may be replaced by self-driving trucks. We've already seen introductions of concepts in that space. So what does that mean about the drive lifespan of the SSD? Is that this change in model affects, for example, what's the ratio of time that the drive is active versus in standby. And so right now we're focusing on the short-term picture of a single owner, single truck driver, and maybe a little bit of drive sharing. And then that gives us a model for how many hours over the lifespan of the drive we need to accommodate. And when you look at things like robo-taxis and self-driving trucks, At that point, we expect that the market will take care of itself, because those vehicles will have maintenance schedules where potentially replacing the SSD at a certain point will be a part of the maintenance of those vehicles. So again, this is the usage models that we're considering and looking at for the development of this specification. Getting down to security, what you see is that you need to have a set of keys that are solid and secure. And so we want to make sure that we're going through this challenge, an authentication process, and then also we want to be growing over time to make these algorithms stronger and stronger to make sure that nobody can hack into cars. So let's think about those other applications. Like I said, we want to grow the market for this to help drive the volume. So let's think about who could use an SSD with a long lifespan and high data throughput, lots of sources in a high reliability ball grid array package, and across a range of capacities. So we started thinking about markets where this could be managed. And this is a good example of how the superset and subset features of the specification would work. So for example, let's say that we want to put this application into an industrial. And in the industrial, maybe you want to put this in an NVMe form factor. So what you might want to do for that market is increase the number of virtualizations. Maybe you don't need 115 degrees C. Maybe you can live with 105 degrees C. And so you start modifying that specification in a way that you've now defined a subset or superset of that device for that market. Similarly, you can put that into a tablet. You could put that into data centers. All of these things have different requirements, but I think what we can do is bring those requirements and enable them in the context of the automotive SSD standard. Again, point being, grow the market. So with that as context, let's think about what are the things that are likely to change. I told you this is a work in progress. And so what we'd like to do is focus on what are the things that are likely to change so that you don't come and beat me up a year from now when the spec comes out looking differently than I described. So one of the things that is in process in the industry in general is a move from PCIe 4.0 to PCIe 5.0. We know that that would double the bandwidth per lane, but it might have some trade-offs in terms of heat, in terms of other complexities, and maybe even more importantly is I showed that there were going to be maybe 3 or 4 SoCs that are sharing that SSD resource. You also have to synchronize with the schedule for all of those SoCs to make the transition from one version of PCIe to the next. So it may be that what we do is we recommend that system designers lay out for 4 lanes of PCIe 4.0, and then as their controllers migrate to PCIe 5.0, maybe they can just start using 2 of the lanes to get the same performance, or maybe use all 4 lanes to get the next level of increased performance. So it becomes a trade-off, but as long as we start with a reasonable superset feature, we can modify that as marketing requirements change. So the other thing that may happen is the security authentication schemes. As security hacking happens, and we realize that over time we need to be able to change with the times, incorporate new authentication schemes, and just fundamentally track where the industry is going on keeping the cars safe. One of the other aspects is that temperature grade. I keep mentioning how the car designers would really love to have 115 degrees C temperature. Flash devices have a tough time, especially with the multi-level cell structures. So one of the things that I anticipate we will be debating is maybe we go with a hybrid scheme where the drive is partitioned into a high reliability portion of the drive and then a non-critical portion of the drive. And so with that, we can have the critical data be supportable up to 115, and the non-critical data, maybe that can be at a different temperature grade. So I anticipate you might see some interesting work in this area of how to scale the functionality of the drive. And then finally, we're going to have continuing debates on the usage models to figure out what the long-term reliability of the drive needs to look like. So this thing looks like a big jigsaw puzzle to me, I'll admit. There are a lot of pieces that need to come together. And it takes time to negotiate all of these features one point at a time. So you realize that we have hours of discussion about the BGA package and what are the options that we want to support and how restrictive do we want to be. We also go in and debate things like the temperature grade, how to do derating, what are the usage models that we have to incorporate into those temperature grades. We have long debates over all of the features, even just the formatting of the specification and how it will reference the external specifications. If we're pointing to NVMe 1.4 and then NVMe upgrades to revision 1.5, what do? We need to go out there, evaluate that, potentially update our specifications based on the changes between 1.4 and 1.5. A lot of work that goes in keeping a multi-standard specification solid so that we don't get out of sync with one another. We do have the agreements in place to talk with these other groups, and fortunately we've had really great participation from a number of people in terms of getting these pieces put together, getting the organizations coordinating, cooperating, and finally we hope to have the specification all put together sometime maybe next year. So it's coming together. It takes time, but all good things do take time. So I'm going to close out the formal part of the talk with a call to action. This call to action is get involved. JEDEC cannot operate in a void. We cannot push to the industry something that it doesn't need. We need to have both push and pull in order to have a successful specification. So I'm calling on car designers, SSD suppliers, all the infrastructure guys to get together, take a look at this specification, join the task group, join JEDEC, and get involved to help make this come together in the marketplace. So what is it that we just went over? Well, we saw that the self-driving cars are introducing a whole new level of complexity that we've never seen out on the road today. They are going to be moving phenomenal amounts of data over these interconnections inside the car between multiple execution units and multiple features. So this new generation of cars is going to need a good solid state drive to provide the permanent storage for these execution units. And now, as you've seen, JEDEC is driving this specification. We will be authoring the master specification. However, it does require the coordination with a large number of organizations. And I'm sure that a lot of people that are viewing this today are going to be involved with those groups. So please get engaged, get your feedback sent to us to make sure that we come up with something that everyone can use. The specification is underway. We're meeting every week for hours to debate these features. And yeah, it's part of the fun is getting people of many different opinions to come together. And going outside the automotive industry to help drive the volumes would be very helpful. If you're a tablet designer and you see something like this could be very productive for your tablet, get the input to us. Don't think of this as just an automotive drive, but also think of this in applications where you can help drive the volumes, take advantage of the work that we're doing to get multiple suppliers to compete for that design, and bring those requirements in as well. We will try to incorporate things for the tablets, for the industrial, for data center applications, whatever it is that helps drive the volumes and helps make this more successful is in everybody's best interest. But I have one final slide as well. And that is, now that I have your attention and your time, I'm going to talk about something that's a little off the tangent here. The tangent is a group called BRDG, Bridge to Connect. This is a nonprofit organization that does mentoring of university students in science, technology, engineering, and math fields. We have an event that we put on twice a year to bring technology people together along with the students that we mentor and talk about some topic of interest to the science in the field. In October, on the 20th, we're going to have an event where Michael Gearing of Raytheon will be giving a presentation called Directions, Applications, and the Future of Artificial Intelligence. Vaguely related to the automotive, but the fact is, I just wanted you guys to be aware of this. It's free. The link to BRDG is shown here on screen. Please come to the link, join in the event, and help support, because we are all getting older and we need to pay it forward. We need to make sure that the next generation of students are coming along to keep the momentum going. And with that, I'd like to conclude my talk. I thank you all for your attention, and I trust that this was of interest to you. Thank you very much, and we'll talk to you next conference.